Real quick before we get started here, the math gets worse in this part. Don't be afraid to skip over the details and go straight to the end for 10 facts about models. After all, we don't really care about this bug. I mean, we do, but we don't. The motion of the bug, part 2. A quick review of part 1. The bug moved. Marks were made. Data was taken. Measurements entered into a table. Displacements were used to find velocities. Velocities were used to find accelerations. These values led us to dots. They showed a bug slowing down, moving at constant speed, and then quickening up the pace. This was one model for the bug's motion. This could be another, but gosh, it looks complicated. This is a third, non-constant acceleration. Is that even allowed? Our focus will be here on the bug from 4 to 8 seconds. A line segment with endpoints. You know what that means? Quick, find a slope, and then we'll use the slope to find an equation for acceleration in terms of time. Integrate to find an equation for velocity. But wait, what's that constant, v naught? Well, one thing we know that the velocity at 8 seconds will be 0.55 centimeters per second. Use that to find v naught. Then take velocity, a good expression there, and integrate it to find displacement. Another constant needs to be found, and we can do that because we know that at 4 seconds, the bug was at 9.2 centimeters. Use that to find x naught, plug it in, and you're done. You have now an equation for displacement born from a changing acceleration. But does it work? Does it give us the dots we want? At least from 4 to 8 seconds? And how close should we expect the answers to be to what we measured? Well, there's the data. And to judge our new equation, we'll have to take a quick look back at some of the other ones we found, starting with a bad model, one with a single constant speed that's not even close. The second model has 6 segments. We're interested in 2 of them, one from 4 to 6 seconds and the other from 6 to 8 seconds. Wow, that's a great fit. But it's kind of cheating. The 3 positions were built into the equations. And what's the velocity at 6 seconds? Should we take an average of those 2 values? The next model, constant acceleration from 4 to 6 seconds, and then a constant velocity from 6 to 8. We had 2, if you remember from part 1, we had 2 different forms of this model. We're using the one that fit the data better, but like the previous model, it does not know what the bug's speed should be at 6 seconds. Velocity versus time and acceleration versus time lead us to model number 4, I think. This time we'll use 3 different accelerations. We'll start from the right. Acceleration is 0 from 7 to 8 seconds. And we know that there the constant velocity is 0.55 centimeters per second. There is the displacement equation, but like before, we need to find a constant. Good thing we have a value for the position at 8 seconds, 1 equation down. The second equation is valid from 5 to 7 seconds. Acceleration is negative 0.2 centimeters per second squared. We write out an equation for velocity to find out the constant v naught. We'll say that the velocity at 7 seconds is 0.55 centimeters per second, that value again. Next step is to use the distributive property to simplify the velocity equation. That will make it easier to integrate. And after you find the constant, we have equation number 2. The third equation in this model, and man, this is a lot of work. And the third equation is only valid between 4 and 5 seconds. Acceleration, velocity equation. We'll use a value for velocity at 5 seconds to find v naught. Then rearrange, simplify, integrate for displacement. 1 final constant to find, and hooray, I guess. I mean, it works well enough. But these 3 equations go squarely into the not worth it category. Finally, though, we can appreciate a single equation for this entire time interval, not 2 or 3, but just 1. And it lines up pretty well, not perfectly, with our values. Remember where this equation came from. We talked about a changing acceleration from negative 0.45 to 0. And then we plugged in one value for velocity to find a constant and another value for position. all of which leads us directly to the inescapable conclusion that motion can be modeled in multiple ways. So unfortunately, we have not learned much about bugs, but we can say now a few things about models, and not all of them good. Number one, all models lie. Even when they line up with the collected data, well, they never do it perfectly. The only thing that perfectly lines up with the collected data is the data itself. And even if the model was perfect, you would never know it. Your measurements all have some degree of uncertainty. 2. The second way models lie is precision. When you start throwing around equations, your calculator can give you long strings of digits, but don't take them seriously. Think about this. How can a model give out values that are more precise than the data which was used to build the model? If it could do that, then you'd know more about the things you didn't observe than the things you did observe. Number 3, briefly put, models are guesses. We don't know what the bug is doing between these points. We can make guesses, but the bug does not have to listen to us. It can go get a cup of coffee and come back if it wants to. Number 4, models mean making choices. For example, when did the bug start moving with the constant speed of 0.55 centimeters per second? At 6 seconds, according to this model, or 7 seconds, maybe 8 seconds. And I know what you're going to say, well, check the data. But your data does not tell you an answer. It can't. You measured positions, not velocities. We're trying to connect the dots, but you can't just connect the dots because there are many, even infinite different ways of connecting them. And keep in mind that the red position versus time dots, that's the data. The green and the blue dots, those came from analysis, not observation. That's not a bad thing, just something to keep in mind. So now, after sufficiently trashing models, let's see how they can be good, and specifically how some models can be better than others. Number 1, correspondence with reality, with measurement. This can be powerful confirmation of a model. I didn't say proof. Powerful confirmation. Matching up with known data is one thing, but providing a testable, high-stakes prediction is even better. And we did this in part 1. We came up with predictions of where the bug would be at 17 seconds. 4 predictions. If we could somehow go back and find a high-resolution security camera footage of that classroom, we could put them to the test, battle it out. Who would win? Number 2, internal consistency. In other words, smoothness. Some of our models provided multiple answers to where the bug would be at any time or how fast it would be moving. In other words, the 2 segments did not line up perfectly. Obviously, both values can't be right, so we'll just choose one. Well, okay, but then the value will be jumpy, like this one, where the bug speed somehow instantly changes at 6 seconds. Number 3, elegance or simplicity. You could, after all, smooth out all the rough spots with more and more patches, but the model is supposed to serve us, not be served by us. In other words, the fewer equations, the better, and the simpler the equations are, the better. Number 4, closely related is power or freedom. Consider this model a great fit, but that's because these 2 line segments were anchored to these 3 position points. In other words, we're not adding any new information. A powerful model tells you things you don't know. It makes predictions. You can't tie your dog to a fence post and then compliment it for staying. When it is free to move and still goes where it ought to go, that's when it gets a treat. Here's an example. I give you a cannon with a known muzzle velocity. You choose the angle, and then you calculate where the ball will land. Then you place the target. This isn't guessing and checking. You only have one shot to hit the target. If you do, I will accuse you of knowing something about the motion of projectiles. Even better, a historical example. If you can predict where the planets will be next year, or when the next eclipse will happen, if you can do that, you're on to something. Number 5, clarity. That's why I found all those velocities, delta x divided by t, and all those accelerations, change in velocity per time. A good model will clearly state what is happening. And if you know that, this goes more for planets and projectiles, less for bugs. But if you can clearly state what is happening, the model can point towards a reason why that is happening.